Hello folks, welcome to Kinetics and Equilibrium. We have a bunch of stuff we're going to be talking about in the next couple of podcasts. We don't have a lot of math in the Kinetics and Equilibrium section, but we do have a lot of concepts. And I think most of them are things that you can understand pretty quickly. So just go along with it and see how we do. Kinetic molecular theory, we need to remind ourselves of what that means. When we look at the word kinetic, what does that mean? See if you remember. Pause the video, think about that for a second. Kinetic, what's it mean? Sure, kinetic means motion. All right, so we're talking about energy of motion or things in motion. Molecular, obviously, is talking about molecules. I don't need to write that down. And theories, this is what we think is going on. Okay? We can't say this is definitely what's going on, but we believe this is what's going on because the concepts all match what we see in nature. Okay? So theory is something that we can't prove. Okay? So the kinetic molecular theory, we're talking about the motion of molecules, and we can't prove it because we can't see the stupid molecules because they're so tiny. So we can't see them. So typically we talk about the kinetic molecular theory, we talk about gases because we think about the molecules of gases and they move really, really quickly and they're very, very small in relation to this empty space around them. They are always in motion, moving very, very quickly. And when those molecules encounter other molecules, sometimes reactions happen. Now, is it every molecule that touches every molecule? No. But certain molecules, when they touch each other, if they happen to do it just right, with the right amount of energy, then a reaction happens. So let's talk about that. We have something called collision theory. And the concept of collision theory says that particles can only react if they run into one another. All right? So, for example, let's think of two people dating. If you never met, then you can't get together and date each other, right? So the particles can only interact, obviously, if they get close enough to each other to run into each other. And what particles are colliding? We're going to talk about different types of particles and when they're colliding. And what parts of them are colliding? Of course, remember that it's the electrons that are on the outside. The electrons are the things that are interacting. Can we make them happen faster? Typically, we think about temperature when we think about speed. Remember, this is something that we've talked about before. And can we get more material to react? Well, we've done that with doing things like stirring things or breaking them down into smaller pieces, that kind of thing. So we're going to talk about those. Right. Let's say that I take a baseball and I hit a window. Am I going to break the window? Well, obviously, if I just kind of lob it really slowly, then probably the window will be okay. But if I throw the baseball really, really hard, well, chances are it's going to go right through the window and make a mess, and that would not be good. Okay, someone's got to fix it. Well, it's probably going to be me. All right. Another thing with collision theory is orientation is important. If I had thrown the ball so that it grazed the glass, even though it did it quickly, like let's say the ball was going vertically, okay, if I had a piece of vertical glass and the ball kind of went like this, all right, even though it was thrown pretty hard, it's probably not going to break the glass. Well, this person over here is not going to be too happy when she hits the water or the muddy water or whatever, whereas the orientation here going into the water is just fine. Well, we have to think that same way about atoms, ions, and molecules because they can react to form products. They can react. All right? They may react, they may not react. So we have to say they can react to form products when they collide with one another, provided they have enough kinetic energy, enough speed, dictated by temperature, and the correct orientation. So we're going to talk about that. All right? Let's think for a second about pancakes. Now, if you make pancakes, you can take the eggs and you can take the flour and you can take whatever else you put into pancakes and mix it all together, right? And nothing happens. I mean, it kind of sits there. It might bubble a little bit, but you're not going to want to eat it, right? So one thing that I have to do is I have to take all the molecules and get them touching each other. So when I add the milk and I go and I stir it all up and I make it into this batter, right? All of the molecules are touching each other, but they're still not edible, or at least nothing I'd want to eat, right? I have to take the pancake batter and I have to heat it up. And when I heat it up, the pancakes have a reaction. A reaction is going on. The pancakes cook. That's called a chemical reaction. And then they become very edible and very tasty, especially if they include chocolate chips, which these clearly do not have. but mine always have chocolate chips. Anyway, so what we're talking about is we're talking about the collision between the molecules. And these molecules are colliding up here, but they don't have enough energy to react. Whereas these molecules are colliding, but they have enough energy because we added heat. And when we added heat, that was enough to make them collide properly. Let's think about water for a moment. If I look at these little white things up there, that's like H2. And we have another one, that's another H2. And this red thing, that's an O2. And when they get together, if they get together right with the proper amount of energy and in the proper orientation, then we get a couple of water molecules. All right, if we think about this, this is 2H2 plus O2 gives 2H2O. And that's what we're seeing here with this thing called an activated complex in the middle. We'll talk about that more in a minute, but they're all stuck together at that point. And they're very unstable, trying to figure out what they're going to do, and then they break apart and come off as two waters. Now notice down here in example B, they are not breaking apart into two waters. So what happens is when they get into this complex thing here, this activated thing, right, you'll notice that both of the hydrogens are on this end, both of the H2s are on one end of the oxygens. So there's nothing reacting with this oxygen. So that oxygen says, I'm not going to break apart. And as a result, you still get water. You don't get water, you get the oxygen. This is O2, and you get the H2s coming off down here. All right, so no reaction happened. You were trying to form water. And in all honesty, this is what often happens. Most of the H molecules and O's, most of the H's and O's are going to react and form water. But there will be some that, for whatever reason, did not have enough energy or did not have the right orientation to actually form water. So what needs to be true to have an effective collision? Or another way to put it is a chemical reaction. Well, the first thing we have to have is a collision. All right, what's the second thing we need to have? What's the third thing we need to have? Well, the other two things you need to have besides the actual collision is you have to have enough kinetic energy. All right, and to have enough kinetic energy, that's temperature controlled. So the thing needs to be hot enough, the thing needs to have enough kinetic energy to make this happen. Okay, so the appropriate energy needs to be there, and the third thing is they need to be in the proper or correct orientation. Okay, so it's very important. Those three things have to happen to have a reaction. Now remember our match? We talked about this in previous podcasts where a match does not spontaneously combust. We have to go and strike the match against something, a little bit of a piece of sandpaper or whatever, to go and make it light, as you see over here. And once it starts burning, it's good. Well, what's happening at the molecular level? What's happening is we have, we're going to call it a fruitful collision or a good collision. We have a couple of molecules. We have a molecule of, call this A2, and we have a molecule over here of B2. It doesn't matter what it is. But when it gets together, if it happens to be in the right orientation, what has to happen is you'll notice you have a bond between A and A right here, and a bond between B and B right here. And right now you get all of these things all together, and when you're done, you have a bond between A and B, and a bond between A and B. The bonds between A and A that used to be there are gone. Right, so what we have to do is we have to break bonds here, and we have to form new ones there. And that's what has to happen at the molecular level for this thing to happen. Now, if we look at water forming, H2 plus O2 giving us water, right, this is the Hindenburg, and Hindenburg blew up, or burned actually, back, I think it was in the early 40s, might have been the late 30s, I'm not sure, 1940 approximately. And it was full of hydrogen. Okay, so this is all H2. This is all full of H2, and it started burning. No one really knows why. They think it might have been an electrical spark that started the whole thing. There's been a lot of conjecture about that. You can look that up online if you want to. But the bottom line is once this stuff combines with the O2 from the atmosphere, which you can't see, right, then it ends up burning all this stuff, and all of this is a lot of heat, but it's also producing a lot of water. So what's actually going on at the molecular level? Well, what's happening at the molecular level is you've got H2, that's H, that's H2, and these two are bonded together. All right. So let's look at what that means. That means I've got H bonded to another H, and they're sharing these electrons between them. And I have two of those, so I have another H, all right, that looks like that. And then I have an O2. Well, O2, remember, oxygen has 1, 2, 3, 4, 5, 6 electrons, and we bond that with another oxygen with 1, 2, 3, 4, 5, 6 electrons. So these guys are actually bonded and shared in there. They've got 4 of them that are shared in O2. So to be able to go from this to H2O, what's H2O? Well, O still has 6 valence electrons. All right. But what happens is hydrogen comes over and shares 1, and hydrogen comes over and shares 1. And we're going to do that same thing with another oxygen and 2 hydrogens, where the hydrogens are sharing those 2 electrons. So all of our electrons are conserved, but what has to happen is that these have to break, and these have to break so that this hydrogen electron can come over here to be with oxygen, and this one can go over here to be with this oxygen, and these guys have to go on the other side. So again, orientation, you can see, is important for those electrons to get over there. So we'd have to have this H2 would have to be kind of over here to make this happen. And the electrons all shift around and get bonded with different things. So we have bonds breaking and bonds forming, and to break bonds, that takes energy, right? Because hydrogen's already happy right like this, right? So all of a sudden we have to break these bonds between these 2 hydrogens, between the 2 electrons of those 2 hydrogens, that's right, and that takes energy. But then it says, oh, I can reform with oxygen, and that's cool, and I'm really happy when I do that. So bonds forming is going to release some energy for us. Now, why is this picture here? Well, just a reminder, what's coming out of the back of the space shuttle there, that's hydrogen bonding with oxygen and producing water. All right, so again, let's look at what's going on. The white things are hydrogen, the red things are oxygen. And over here we have some reactants. So this is H2 plus O2. In fact, it's 2H2 plus O2. Over here we've got a bunch of hydrogens and a bunch of oxygens. And then up here at the top we get this thing called an activated complex. And this is the most unstable and the place where you have the most amount of energy. If you look at this, this is energy going up the left-hand side. So the thing where we have the most amount of energy, which is here, when that happens, we have this thing called an activated complex, right, which is the whole shooting match all stuck together. And then all of a sudden it says, oh, I could be so much happier if I went and broke apart into 2 water molecules. And when that happens, the amount of energy of the products is much lower, and it gives up all of this energy here. You say, well, why doesn't it go all the way to the top? Well, remember, you have to put that energy in. It's kind of like striking the match. You had to give it enough energy. In the case of hydrogen and oxygen, you had to give it enough heat so that the hydrogen and oxygen bonds, the hydrogen to hydrogen bonds could break. The oxygen to oxygen bonds could break. Right? And you'll notice essentially if I draw a horizontal line through this whole mess, right, I've got 2 hydrogens and 1 oxygen on the top and 2 hydrogens and 1 oxygen on the bottom. They break apart to form 2 water molecules. Right? And they give up all of this energy, and this energy right here we have referred to in the past as delta H, our change in enthalpy of the reaction. So that's all, we're putting stuff together here when we talk about this. All right, so let's quickly draw the concept of a Lewis structure for carbon and O2 and how it makes CO2. Why don't you pause the video, see if you can do that. I think this is the last slide. Give it a shot, see if you can do it. All right, let's see what we have. We have carbon and we have O2. So let's see, carbon just has 4 electrons around it. And oxygen, if you remember, is in column 16, so it has 6 electrons around it. And what it does is it bonds with another oxygen with 6 electrons around it. They share 2 pairs of electrons. So this is what happens. So when we're going to come over to have CO2, the two oxygens are not going to bond to each other anymore. So right in here, we need to split them up. So each oxygen is only going to have 6 electrons, which means it wants 2 more. So what has to happen is when I have carbon and I have O2 hitting it, kind of like this, these things have to hit some way to break these bonds. Now, what is the orientation? Frankly, guys, I have no idea, all right, because I can't see it. But as best we can tell, these 2 bonds have to break here. These electrons have to split so that one of them can go over here with carbon and one can go up there with carbon. And these guys have to go on the other side to be with those guys. So you end up with carbon still having 4 electrons around it, right? But now what happens is you've got an oxygen over here with 6 electrons around it, and you've got another one up here with 6 electrons around it. And so you end up with a double bond in between carbon and oxygen, and a double bond between this carbon and oxygen, right? So the way we draw that would be something like this. Well, we can put the spare electrons out there if we want to do Lewis dot diagrams to demonstrate what carbon looks like. It is a linear molecule. All right, folks, that's it. Go ahead and do the worksheet. It shouldn't take you too long. It's kind of cool with some baseball analogies and stuff. We'll see you in class. If you have any questions, let us know. We'll be happy to help. Take care. Bye-bye.